get started shortly. This is our second last class, except for the exam, except for the meeting for exam. We have 2 classes, including today's. So we are very close to the end of the semester. It is time to start thinking about projects. Of course, at the same time, you'll keep learning and finish learning the last subjects. So make sure you let us know if you have any questions as you start, as you start your final project with your team. Let us know as soon as you have questions. Don't delay. Start as soon as. I would say I highly suggest that you do not start 3 days before it's due, because it is going to be a lot of work, and you want to allow yourself enough time to be fully indulged with the project process. Okay, so now will be a good time to start thinking about it. All right, let's get started. So I have already shared my screen. Can you confirm that you can see the slides?
Yes, we can see that.
Okay, thank you. All right. It's a 12th class, 12th week, 8th class meeting, I believe we have had. And I hope you are well on pace with the course progress. Over the last 3 weeks, you were on schedule to study module 7 and 8. And these are, in this course, module 7 and 8 are the very core of supervised learning using 2 different kinds of target variables: a continuous or interval variable and a binary dummy variable. In those modules 7 and 8, the emphasis was more on continuous variables, I believe. And in the final project, oh, sorry, let me revise. I believe the focus was more on binary variables, and then in the final project, the emphasis will be slightly more about binary variables or continuous variables. Okay, so plan for today's meeting is mostly to go over key parts and key points within these modules, the several modules that you have been studying in the past few weeks, as you wrap up and move forward to the final stages of the course to put everything together. Module 9 is to put everything together. Module 10 is to deal with the very last phase of a data mining project, which is data mining project process, which is implementation or deployment. By using your model by using the best of your models to make predictions on the score data set. Of course, cleaning and pre-processing the score data set is also part of that scoring process. And that's module 10. So the points that we'll go over today are very important to the especially the training and evaluation phases of the project. So we'll go over that, and in some of those points, we'll tie that with programming sides, the hands-on part, and to kind of remind you about a few things that that you would wish you have known if you didn't know about that before you head into the final project. And then after that, I'll talk about Hackshot for just a little bit. I'll only make one note about Hackshot for a specific question in that, and that is because I don't go through the whole thing because it is mostly straightforward. It has a large component of the conceptual problems. By this point, I would imagine no problems in your understanding and learning of those concepts. So I will only make one note about the hands-on part. And by that, we will conclude today's session. Any questions before we start? All right. So here is a point about module 8. Now, module 8 introduces another classic machine learning algorithm and go through the key parts of the algorithm and how to do it hands-on with the real data sets. So that's module 8. But also module 8 demonstrates how to deal with overfitting and usage of cross-validation in that nearest neighbor algorithm context. And so this topic here is about dealing with overfitting using cross-validation. So it potentially is related to module 7 and 8 together. And then the whole project, the whole problem itself. So for predictive analytics for these projects, the goal is to optimize the performances of the model with regard to data that were not exposed to the algorithm. That's what we call unseen. It's what we call unseen data. It's out of sample data. By sample, we mean training data. So out of sample data, or we say testing data in the train test, framework. So all of those are what we mean by unseen data. Do you agree? Or is there any problems with? I would like to hear some responses. Do you agree?
Yes, I agree.
Okay. Anybody else or any different opinions? Well, yeah, that is true. And, this is the background. This is what we try to emphasize, right? Otherwise, if the algorithm is not able to perform well on data that the algorithm was not exposed to, how would you expect the algorithm after training to be useful, right? That's intuitive. So the true or false is actually not for that background, but for the following statement. So think about it. In order to, this statement goes like this. In order to avoid overfitting, you should never allow the training models to be over complex. So complexity is neither good nor bad in the absolute term. Complexity is good because it can help solve underfitting that we talked about. The model is too simple, there could be underfitting problem. On the other side, if the complexity is too much, what it does is it could allow the model, the complex model, it could allow the model to very easily pick up changes or correlations, intricacies in the data that is purely attributed to randomness. But since the algorithm has no way of differentiating what is pattern and what is noise, by noise we mean randomness. It's only the pattern, the real correlations, underlying correlations between the input and the target. That's the phenomenon we want the model to pick up first. But complex models make it very easy for the algorithm to pick up what is beyond pattern. All right, so over complex models tend to be overfitting very quickly. So with that background, evaluate this statement. You should never allow the trained models to be over complex. It sounds okay. It sounds logical. What is over complex? It's hard to tell, but being over complex is kind of never too good. But the statement continues. In other words, you should start training. Now, so here is talking about the training depth or the amount of training, the time or the iterations or the steps or let's say sometimes we call it epochs for neural networks. The steps or the amount of time or the depth of training that you allow the model to undergo before you stop it. That's what it tries to refer to. It says you should start training the model before they become overfitting. What does it mean before they become overfitting? Which means I will need to bring up the fitting charts that we talked about, and I'm going to denote error on the y-axis and then the complexity on the x-axis. And on the training set, the course materials talked about that for the training set, for the training set, the error should have moved it over. And okay, maybe let's do this. The training set. Initially, the error without training too much or without any training, the error is kind of high. As complexity increases or as the amount of training increase by using this algorithm on the same data set, the train set, the error will tend to go down. And as you continue to increase complexity or continue to train the model, it is going to display a nice, sometimes not nice, sometimes not smooth, but overall will be smooth curve. And we talked about that the error of the training set will tend to go monotonically lower if you plot the error of the model. So that's that. But on the other side, when we have a split sample, when we reserve the testing set or validation set to test the model, the error initially will be very close, sometimes higher, sometimes lower, give or take. Those are never guaranteed. But as you train model picks up the same patterns that is, that displays in both the train and test set. But as the complexity increases of the model, or as you train the model more times, it's going to slowly pick up those noises that don't apply and start to hurt the performance of the model on the testing set. So the rate of increase in model performance or rate of decrease of error on the testing set is going to decrease. The rate of decrease is decreasing. That's one. The slope is reducing to the extent it might flatten. And then as you keep training more, it reverses. So this is a classic fitting graph that we talked about. And this is the test. Anyway, let me continue. So with the test sets, you are able to identify the point at which the model is optimal, meaning it is able to reduce the error rate or optimize the model performance on the unseen data or testing set. And then the bottom of the curve or the turning point would be when the complexity is optimized. That's denoted by C as complexity star. It is this point of the model that you want to select based on the fitting curve model performances on both sets of data that you would, declare the best under this comparison. All right, so with that framework, let's evaluate this statement. First of all, the first part is still generally okay. Probably not never, but it's not too good to be overcomplex. Of course, overcomplex, if we interpret overcomplex to be in this area, then it is not too good. Although it, you can sometimes go there. If you don't, you're not able to plot this graph and see clearly, right? And that's the essential point that I'm going to emphasize in evaluating the second half of the statement. In other words, you should start training way before they become overfitting. What is overfitting? Which area is overfitting? This area, beginning this line, onward, this is overfitting area. Okay, so if the statement said you should start training way before, which means way before, go back, and then stop here. Stop here, way before it becomes overfitting. Stop here and stop shooting and evaluate model. So what happens there is that you're going to observe that the model is performing increasingly better on the training set as well as on the testing set, and the momentum of the model at this point, the momentum of the model shows that it's likely to be better if you keep training just a little bit, right? If you stop here, I can guarantee you the model that you pick is not the optimal one. Right? Makes sense? So in order to pick the best model possible, you would want to allow the model to be overfit, maybe just enough before you stop. And let's think about it. What if you allow the model to train and to be much overfit? Somewhere here, this is quite overfit. You know, what is lost is probably time and computational resources. But what is gained is a clear-cut, nice and clear, interpretable fitting graph that is helpful to back up your decision of picking the best model here. So, you know, the trade-off is there. You allow the model to train a little bit more in return for a clear fitting graph for interpretation and decision making. So the trade-off is not too bad, right? Of course, in general, if it's clear at this point, you wouldn't go to this point. If it's clear at this point, you wouldn't go to this point. So stop, you know, just enough so that you have a clear, interpretable fitting graph. So that's the point. Because of the second half of the statement, this is going to be false. You should not stop way before it becomes overfitting. You should allow the model to be overfitting just enough to see where it's the optimal model. So that is all that's going on here, and that's all I would like to explain. Any questions here? All right. Good. Conclusion's good. And one last point about the fitting graph. So I emphasize several times that pay attention to what measure or what kind of measure is used on the y-axis. And generally that can be two buckets. So bucket one, bucket two. Bucket one is error, like here. And error is a generic term. And there are different kinds of errors, which I'll talk about briefly. The other is performance, or sometimes we say accuracy. And these two buckets are kind of the reverse of each other. If the model commits more errors, the performance is generally lower, and vice versa. So you can imagine that if we use any of the error metric to plot the fitting graph, you would generally expect the training set line to go down continuously, but the testing set or the unseen data or pulled out sample, whichever term you give it, the curve is going to reverse, initially go down, but then reverse course, and it's going to be convex typically. And how to choose the best model, the bottom or the turning point on the testing set curve. But if you opt for using model performance or accuracy to plot the fitting curve, so if this is performance, and then same thing with complexity, then you would expect both lines to start low when the complexity is low. The one is randomly higher than the other just because of randomness. And the training set is going to, I'll pick this one. The training set performance will go up dramatically and then slow down, but keeps going. This is training set. But then for the testing set, it goes up initially, but quickly slows down. The rate of increase slows down to the point that it flattens and then it reverses. So that's the tests or pull down set. So you can expect, the fitting graph to go accordingly based on the type of metrics that's used. I hope this point is clear. The two is completely, vertical mirror with each other. And under the error, although we don't cover that many different concepts here in this course, because this course we needed the first half completely focused on Python. So we don't have enough time to go into model evaluations too much. The most that we use is mostly for continuous variables. We use sum of squared error, and for binary classification problems, we use misclassification error typically. So we have sum of squared error. You know what I mean? Sum of squared. Not recommend that, but sum of squared error. And we also have misclassification error. And then there are other kinds of errors. And sometimes error we use cost to express error, although they don't correspond to each other exactly, but still. Let me see. I might have a change. Okay. Anyway. We have, so for cost, we have loss. We use loss to stand for error as well. And we have other specialized errors. We have false positive error and false negative error. We don't go into details in this course, but we go into details in the framework course. For model performance, we have accuracy, exactly the number of accurate hits by the computation algorithm. Well, what else do we have? We have recall. We have precision. And we have what's called specificity. Again, we don't go too much into these details, but even if, let's say, even if a homework question or exam question talks about these, it's going to give you the explanation, going to say that this is a performance measure. So be able to differentiate the shapes and types of graph, the fitting graph, according to the type of metrics that are used on the y-axis is critical. All right, that would be all for the fitting graph, and nicely showing the mirror version of the fitting graph, given that the y-axis uses an accuracy measure. Training continuously goes up. Testing set reverse. It is concave in this case. The turning point would be the point where the model is optimized in terms of performance on the unseen data. All right. All right, now cross-validation. In this course, in the hands-on part, cross-validation is emphasized because with cross-validation, so typically for demonstration purposes, I either would opt for Turing test split or cross-validation, or use X cross-validation. I typically don't demonstrate both at the same time because it tends to confuse students, and I'm not saying you cannot use both. You actually should, but that increases the complexity of the project management process. So I don't advocate, as you're learning, I don't advocate doing them in the same project. But typically, train test split happens very early in the project process. And for those students who are enrolled in this semester, enrolled in the framework course, I have talked about this in detail. I have gone through this conceptually as well as hands-on, how to use programming to manage the different data sets. But essentially, train test split happens very early on in the project process, whereas X cross-validation is typically used in within the training, model training, as well as evaluation process. Cross-validation nicely mingles the two together and eliminates some of the steps that would have been necessary under a train test split framework in selecting the best model. So that's why in this more programming heavy course, we use cross-validation to streamline the process more than otherwise. So with cross-validation, what's important here is the quality of cross-validation. All right, so cross-validation is supposed to be handled by programs, by programming or by computer software to to shuffle and select data sets as randomly as possible. So that is the purpose. If you cannot take samples or take subsets randomly, then you cannot be sure. You could not have high confidence that the differences between the models are because of the both the complexity and overfitting of the model. It could be other factors. So it's like experiments. If you don't ensure enough level of randomness in cross-validation sets, then you have a third factor to, to significantly muddle the pond so that you cannot be sure that the model that you selected is the best. So with that background, let's evaluate these statements. Regardless of the type of cross-validation techniques, plain text split, cross-validation tenfold, fivefold, let's now focus more on the splits of the sets. And we'll evaluate 3 statements. And let's see your thoughts about whether or not they are fine or problematic. The focus here, whether or not it's fine or problematic, the focus here is whether or not you can be sure that the randomness is implemented or the randomness is done sufficiently. So let's take a look at the first. A marketing data scientist is doing a predictive modeling on customer spending patterns, and this data scientist sorts the original data set. Let's say this is the training set. The original, this is the overall training set, which you're supposed to split into train and test or use cross-validation. He sorts the original data set by age, beginning with 18 and ending with 90, 95, for instance. And then after sorting, she partitions, which means segments the data into 2 sets. 60% on the top, assign it to training set, and which is used for training the model. The rest 40% on the bottom, assign it to testing set. Think about it. Is randomness in assigning the data roles into training versus testing set, is randomness done sufficiently here? And why or why not? What do you think?
Yeah, his training data set would be problematic because he won't have the older population in there.
And what about the testing set?
It's not random because he's selecting from top and bottom. So for data set to be random, it has to be selected randomly 40% or anywhere in the data set. For testing set.
It is a good point. it is a good point. The point is on whether or not you assign these rows. You know, imagine a data set where we have a header and then we have different rows. We're putting these different rows into either training or testing set because you cannot, you cannot reassign the same row into both sets, right? It is the selection of the rows and assigning that into either a training set or testing set that is problematic, right? That is the point, right? And just to be clear, 60% into training set, 40% into testing set is not a problem. You know, is it the best? Maybe. It may not be the best, depending on the circumstances, but it is definitely fine. In fact, many projects use the 60-40 rule. There are considerations to argue for a larger training set. It would be better, but those would be certain circumstances. Here, the split between 60-40 is not a problem. The problem is the assignment of the roles into which and which other. And logically, it is what the first student said, that the training set would have those customers who tend to be younger, because in the ascending order of age, those on the top tend to be younger, 18 to 50. Whereas those at the bottom, with age between 50 and 90 assigned to the testing set. So if age, there are two scenarios where this would be badly problematic. In the first scenario, age is an important direct attribute that that relates to the target variable. Here, it's the spending amount. Older people tend to have more money, have more budget. You know, that's a general rule. So you would end up with those with less spending power in the training set, and those with more spending power in the testing set. If age is a critical input variable that has predictive power, then the model is not going to, the model is going to have a large bias. It could de-emphasize the role of age, the power of age. Or the other scenario where this also can go wrong is when age is not a direct predictor, but age has correlation with something else, which is not in the data set, but that something else tends to be highly predictive of the target variable. In both these cases, this way of assigning the data set into training versus testing set is going to be problematic. All right, well done. Let's take a look at the second statement. Now, the same data scientist, let's say another data scientist, just to be fair. Another data scientist, after sorting the original data by age, the same sorting, then takes a random sample. How does he do that? He uses a randomizer. He uses a random, let's say a random number generator to assign a random number to each row. and then only take those rows with that random number. Typically, the random number is between 0 and 1. Between 0 and 1. So to get 60%, you simply pick those that are smaller than 0.6. Smaller than or equal to 0.6, which is 60% of this band, this range. He takes a random sample of 60% of the rows without replacement, meaning without duplication, into the training set, and then the rest into the testing set. Is he doing anything wrong this time? Why or why not?
It's fine because the random number becomes like a new ID for the column and we're picking at random.
I would agree. And then the sorting by age is kind of it's not doing anything here. You know, because by any kind of sorting, as long as a random number generator is involved about the rows, then the sorting does not really matter originally. So this time the data scientist is fine in doing this. Any questions? All right, let's look at the last. Another data scientist scrambled the rows, meaning randomized, meaning assigning a random number in the new column and then sorting the rows by that randomly generated number. And the result of that is the rows are scrambled. It doesn't follow any particular sorting. It's sorting by a random number, which means random sorting. So the rows are scrambled. After that, the top 60% of the rows after the data set is scrambled are assigned to the training set. Whereas the other 40% were assigned to the testing set. Is this fun? Why or why not?
Yeah, both second and third options are fine because in both we are selecting random numbers. We are not sorting it, although because in the third one the rows were scrambled, so it's no more a systematic or sorted row or ascending or descending order.
Everybody agree? Any objections? I agree. Essentially, the focus is randomization. Is the partition done with the randomization step immediately preceding it? That is a key point, right? I think this class wouldn't have an issue in judging whether or not the assignment is random. So we're going to keep going. But do let me know if you have any questions. So that would be all conceptual points that I would like to highlight for overfitting and cross-validation. Here's a few points about the coding and potentially making it easier for you after you have learned so far. So I emphasize sanity checks a lot because data analytics using programming, especially you know, with tools like Python, which is not as visual as R or other enterprise softwares. It's less visual, it's more abstract. A lot has to happen in your mind. And you cannot, and I also don't suggest you look at the data all the time, because with large data sets, especially with large data sets, you cannot look through the data set. You know, it's just not, it's counterproductive. So that's why the importance of sanity checks becomes higher. You want to design your sanity checks. Over time, you build a routine or you build a habit. And that's all, you know, I would like to emphasize that should happen on your side. By knowing how to conduct efficient sanity checks, you can essentially avoid problems and be more highly confident about the outcome of your steps, whatever it is, cleaning data, pre-processing, cleaning the models is less relevant. But after cleaning, you'll evaluate your data set, you'll evaluate the performance of your model by comparing the predicted values with the ground truth, the true labels. You will calculate value model evaluation metrics, and then after making predictions, you will, you know, add that predicted values into data sets for execution by the management team. All of these involve data wrangling, data management, copying of a column, moving of a column, matching, merging data sets, you know. So in all these steps, data are moving. How do you make sure things go as intended? Sanity checks would be the Omni tool that should be in your inventory, that you use them as much as necessary. In one kind of sanity checks, you check before you copy a column, that could be a series that is because of some filtering process, maybe, or because of calculating a statistic of different columns. Let's say statistics. Let's say the mean or the average. The average of all the columns of a data frame. When you get that, you get a series. Now you want to add that series into a different data frame that records other statistics about these columns. You want to make sure that the shape, the number of rows in your series is the same as the number of rows in the data frame, and you want to make sure that the row indexes match. So you cannot I mean, it's counterproductive to use a for loop to compare, because you would have to come up with some kind of metrics to summarize the level of matching, you know, between especially the indexes of the two data objects. So the best way I have come to use or develop, and then, you know, try different things, but over time I come back to this over and over. The first version was this, that I take the index of the first data object, maybe a data frame, and then the index of the second data object could be a data frame or a series. I take those. By the way, how to get the index? It's the dot index. and no parentheses, because this is an attribute of the data frame or series. Take the index object of the two data objects and use unequal evaluation to compare them, to identify anything that's unequal, element wise, pairs of elements. Anything, if anything is unequal, then it's going to be return true. It's a Boolean series, and then use sum to get the total number of mismatches, and then I evaluate that sum with 0. If it's not 0, if it's anything other than 0, something does not match, and then I should not go ahead and copy. I should investigate, because I expected them to be true. If it's not true, if there's any mismatches, I should investigate something for them. All right. So that is the first version that I, kind of just start using over and over. And then instead, alternative version would be to use NumPy.sum, but essentially these logic is the same. So I keep using either of these. And then over time, I realized that I don't have to take the sum and evaluate with 0. I can use other methods, like any or all. Would be something that is more elegant, I would say, less, less like this, by looking at this, if a second person looks at this and then is trying to figure out what I'm doing, if I don't put notes there, it may not be immediately clear. But these versions are more readable. I'm evaluating whether any of this big series, after evaluating their inequality, I'm evaluating their inequality. If any element-wise comparison turns out to be unequal, it's going to evaluate as true. So any true is bad, right? Think about the logic. Any trueness is bad. So if there's any inequality, it's going to evaluate true. True is false, I'm going to get false. I'm expecting true, but I get false. There's a problem. But if nothing is unequal, everything equals element-wise. If everything is equal, there's no unequalness, then it evaluates as false. False is false, it becomes true. Send the check passed. So that is one way. If you use equality to evaluate, then you expect everything to be equal. So .all. If everything turns out to be true, .all will evaluate as true. True is true, returns true. Sanity check is passed. So these are a few tricks that these tend to be the ones that I use more nowadays than that. And nowadays something I also use is assert. Assert command. Assert command will throw an error if what is being asserted is false. So you can pick these and to assert. If it evaluates as true, which means the two indexes are exactly the same, element-wise, they're exactly the same, then assert will pass, and there's nothing happens. There's no evaluation. There's no return. For these two, it's going to return true or false. It's not going to throw an error, but it's going to evaluate as true or false. Here, if it's true, nothing happens. That's good. Silent. But if it fails to evaluate as true, then it's going to throw an error. You know, those error those annoying error that some of you, are fearful about. If they throw an error, that means sanity check is not passed and you need to investigate. So I use assert quite often now, but it doesn't, it doesn't affect it. It's a matter of taste. So either use this or that as sanity check will be my best practices. Any questions? In the early stages of data pre-processing, I talked about get dummies. Get dummies are used to convert categorical variable or several variables into groups of dummies. For just one categorical variable, you'll get one group of dummy. For several categorical variables, you'll get several groups, several bundles of dummy variables returned in the same data frame. So that cuts down, manual labor in pre-processing those. But later on, we use transformers. So we kind of is not using get dummies a lot. But just one note that there are two get dummies if you search Google, since we use Google a lot. There's a Panda version, pd.getDummy. pd.getDummies. There is nothing that is, let's say you have a DF, you have a data frame. You have a data frame 1, let's say. You have a data frame, and then you call get dummies methods. There's no such thing. Okay, there's only pandas that get dummies, and you provide the series or the data frame. This is the one that you want to use if you pre-process the data sets, the training sets, using more of a manual process, which I just discourages. But just in case sometimes the pre-processing is straightforward, and then you can use get dummies occasionally. In that case, you want to use pandas that get dummy, but not the other. The other is you can call series.string.get dummies. This is a completely different method that serves a completely different purpose. Even if it might show up in your Google search. So for the purpose of this course, this is not the one that you want to use, and then pay no attention to it. If you're curious what it does, go ahead and search Google and find that out. It is under series only, series, and it's a string package method that deals with some kind of parsing functions. So, which I'm not going to talk about details here. All right, this is one point. And a last word about using transformers. Since using transformers and pipelines is the way to go in pre-processing the several data sets, the training sets, the validation set, and the score set in predictive data mining. After you have prepared the transformer by which the scalar is one kind of transformer. Transformer is a large group of very similar data objects. And scalar is, we have a imputator, for missing values. We also have one hot encoder. All of these are transformers, and pipeline that does several things in a series, several things as in a sequence. Finish one job, pass the outcome to the next step, and then let it do another job, and then a sequence of operations. That's a pipeline. Pipeline is a group of transformers. Here, using standard scalar as an example, you are going to train or fit the scalar or any kind of transformer on using training set. And then after fitting, you get the statistics of the relevant columns from the training set, and then transform, which means to prepare. When you fit the scalar or transformers on the training set, it doesn't do anything to the data set. It simply calculates and remembers and stores the statistics. But it's only when you can transform the training set using the fitted transformer or scalar, it's going to change, in this case, rescale the training set and then return the rescaled training set. So by using the fit transform method of the scalar or any kind of transformer objects, you kill two birds with one stone. Fit transform. Of course, you can do fit and transform separately, but the result will be the same. After you have trained the scalar or transformer, it remembers the statistics from the training set, and then you should use dot transform. Never fit transform to the testing set or the validation set or the score set. You should only use dot transform on those sets, because those are not meant for training these scalars. All right, that's that's straightforward. Just want to make sure you understand this. When you go through module 9, that illustrates a complete process of the first 5 phases of the CRISP-DM process, but mostly the 3rd to the 5th, beginning with data preparation, and then data, or maybe a little bit of stage 2, data understanding, data preparation, modeling, evaluations. These 3 or 4 stages of the process model, that's module 9. You will notice that when using transformers or pipelines, it uses fit transform on the training set and then transform on the testing set. And in module 10, you'll also notice that on the score sets, it only uses dot transform. So pay attention to that when you go through the last 2 modules. Any questions? We are getting very close to the last point. Here, just a reminder, final project due in slightly more than 2 weeks, I believe. Slightly more than 2 weeks. Yes, so, like I said at the beginning of the class today, now is the time to start digging into the project, and let us know as soon as you have any questions. All right, Hackshop 4 is due today. if you have taken a look at it and be prepared, that it will be super. You will be able to, I believe, turn it in by the end of the class. But no worries if you need more time. As long as you turn it in by the end of the day, it is no problem. Homework 4, no, let me revise. It's not homework 4. Hackshot 4. Hackshot 4 is an individual work. It's not a teamwork. It is not a teamwork. You can discuss, but never copy or, never copy or reuse somebody else's work. A quick note about Hackshot 4. I'm going to switch my focus here to the Jupyter Notebook. And so I'm going to share the other screen. Can you confirm you can see the Jupyter Notebook?
Yes.
Okay, thank
Yes.
you. Thank you. Now, as I said, this hackshot is mostly straightforward because it has a large component of conceptual questions, and some of these I even talked about just now. So I imagine no problem for this class. To answer the first question, for formality, simply double click and you'll see the raw syntax of the markdown. I have included some of the HTML, some of you might be familiar to control the style. For each of these two questions, the green or the red line, one should correspond to the training set, the other is test sets. You can answer the question by typing after the period or before the break, the line break. And then the last line, don't worry about the line break anymore. I'm just going to randomly pick. This does not mean that's the solution I'm randomly picking. Okay, why do I do this? 4 X's here, this stands for my answer, and then 3 X's, my answer, and then run it. I will see your answer here. So do it like that. That's just one way. If you want to add another markdown cell below and then type your answer, the green line is what's sent, the red line is what's sent. Feel free to do that as long as it's clear. Anyway, it's fine. For all the other conceptual questions, it's true and false, mostly some of the short answers. Again, double click to show the syntax and then type your answer below. After that, you'll see a line break, because there are 2 line breaks here. Okay, so the format is taken care of. No worries. 6 conceptual questions, and then brings us to this one big hands-on problem. It talks about the background of the data set and then import the packages. I like to talk about question 8, but in order to do that, I will have to first complete question 7. Question 7 is a simple question. It asks you to read in the data and do some quick sanity check. There's no hard requirements here for the sanity check. Read the data set aside and assign it to DF quality. So I've already written here in the Hackshot that you download, these are blank. I simply typed in before the class started. All right, after I do that, I'll simply check the shape as close to 5,000 rows and 12 columns. Everything is done. And now brings us to question 8. I added these empty cells because I will need to use them. Feel free to write everything in one cell. I also added these before the class. You should see a blank cell here. So this question asks you to check if there is any missing values. If there is any, determine which column has the missing values. And my real point is about the second part of the question, or the third part. Use appropriate method to impute the missing values, which means to fill in those NA. And then after filling those missing values, gives the output data frame as MyDF no NA. And then sanity check the MyDF no NA. Make sure there's no missing values. All right, as you already know, to check if there is any missing value, if there's a large number of columns, then what you want to do is to double sum to get the total number. If you don't really care about, if you don't immediately care which columns has missing value as a first step, if there's no missing value, of course, no column is going to have any missing value. So this is typically the first step. And if I do that, I see that there is one. So there must be one and only one column. It's not going to be half a column that has half is the missing value. It's only starts with one. So there's going to be exactly one column that has exactly one missing value. So the question is to determine that column. So then I backtrack and delete one summing operation, and then I get a series. Actually, this is the outcome is a series of values recording the total number of missing values under each of the columns. And what are these? The fixed acidity, volatile acidity. These are the original columns of the data frame. But in this series, what are these? Can anybody tell me? These are different attributes of the wines, but these are in this data object. What are these? Sorry, I missed it.
Columns?
These are, remember, this is a series. What is a series? It's one column object. It's a vector.
Indices.
So these are what?
Flag variables.
Can you repeat?
Flag variables, categorical variables that is changed into flag.
Not really. Let me do one more thing. The original data frame has these columns. The columns names are fixed acidity, volatile acidity, citric acid, that correspond to each of these. So in this data object, if I name it as X, this is X. X is the data object. In this X, what are these? Fixed acidity, volatile acidity, etc. What are these?
Do you mean independent variables or something like that? That's what you're asking?
Indexes?
Not in this context, but these are variable. Yes, in the data frame. But in this series, what are these?
Index?
Indexes, exactly. These are the indexes of the index. sorry, these are the indexes of the series. And let me show you how to get the index of this series. That is index. So, be clear about that. Now, once I have this, what you can do to answer the first question is column total sulfur dioxide has the missing values, right? Has exactly one missing value. And I would like to just show a little bit more. And this is not necessary, but this comes in handy sometimes. Remember we talked about filtering and using Boolean indexers. Remember we talked about that when we talk about data frames and different kind of maneuvers and wrangling of data frames. You can use X to construct a Boolean indexer and use that to select only those columns, not columns, only those elements with that index as the output that satisfy this condition. The condition is X is larger than 0. Now think about it. What does it do? When you compare X with a scalar, the first thing it's going to do is to broadcast. It's going to compare every single value of the series with 0. Okay, that's the first thing it's going to do, broadcasting. And with that broadcasting, it's going to return another series. It's going to be, this is the series, the return, the outcome. This series with the evaluation outcome, it's going to give you as many elements as this original series, X, and then it's going to say true, false, true, false. In this particular case, it's going to say false because 0 is not greater than 0. False, 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 true. 1 is greater than 0. False, 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 false. So what I can do is I can use this parenthesis because it's an evaluation statement. I can say this is the Boolean indexer, or I sometimes do indexer Boolean. All right, so it's true or false. And then I can make use of that to select X. And then in this case, I will use log, because with log, you can give a Boolean indexer and select those rows. With ilog, you cannot do that. We use .log to select using this Boolean indexer and observe what happens here. Only one thing turns on. This is still a Boolean. This, let's say I assign it to Y. In the wrong button. This Y is another series, but only has one element, and its index is total sulfur dioxide. And with that, you can sufficiently answer the question, right? Then the second question is done. Then with this Y, it becomes easier. Use an appropriate method to impute the missing values. Now, there's a manual way and there's an automatic way. And I would personally prefer automatic way, less costly, right? And more and less labor, more streamlined. So what we do is we leverage the two dictionary of method of series. Remember, Y is series. And what does it do? So hang on, it's not Y that series, but it is series. it is a method of the series, but not from Y. But we need to calculate the statistic by which we use it to impute. So, and since Y here, and not Y, since all of these columns, all of these variables, other than quality, in fact, quality is also an interval variable. All of these are interval variables. So what statistic do you use to impute missing values of an interval variable? You would use median, as we talked about, because median is less affected by skews, or we call it outliers, right? So we need to calculate the median statistic for this column, So we need to get the original column to calculate median. So this is what we need to calculate median. What is this median for? It is original data frame, and then the column of total sulfur dioxide. When I get the median, I get a series, right? The return it is not actually a series. Let's see. If I have a series, I calculate median, I get a scalar. The trick here, but to make the process less manual, if I do this way, I'll need to copy and paste or type in manually 134. How about I use some kind of a dictionary to remember the median of potentially more variables, and then to impute according to the variable name. So that would be more streamlined. For just one variable, the trick is to add another layer of square bracket. So in this way, what you select is not a series anymore. You're selecting a one-column data frame. By doing that, when you calculate statistics, you get a series, but the series has only one element. Let's take a look. You get a series of only one element, and this is the result of the median for this column. And this is what we need. And after getting this series, that's what it means here, we call two dictionary. And the result is I get a dictionary that has key and value, right? By using this dictionary, imputation is done very elegantly, and here's why. Let's say if we have DF quality, and then we say, typically, the immediate solution that one would think of is to select the column where there is a missing value detected, right? That's the immediate reaction. To select that column that has missing values, and then to use fill NA. And then, provide with 134, that is the manual way. A slightly less manual way is to provide this. So let's give it stats impute, and stats impute has only one element here, or has one value prepared for total sulfur dioxide. So I provide that. That's for imputes, and I will get a data frame. Typing error. I will get not a data frame. I will get a series with the missing value imputed. It's not clear here, but if you use is an A that sum. That is strange. The reason could be that when you call fill NA with a series, you end up assigning the parameter to a different thing. If I try this, okay, now that does it. So this is with the default parameter. If I were to be more explicit, problem can be solved. But in the sake of time, let's call the fill NA method of a data frame. This is a one column data frame. With that, when we call fill NA, it is willing to take a dictionary, potentially with multiple entries, with multiple values. And then it is going to only impute missing values for a column with the stats of that column name as the key of the dictionary. So it's targeted. It's it matches the label. It matches the key of the provided input value with that name of the column to impute the missing. So if potentially you don't even have to worry about providing the right thing as long as the dictionary is constructed correctly. So to clean up the process, what we want to do is to calculate the median of the columns and then provide the medians to the data frame for imputation. And then hopefully the imputation process can fill in the corresponding statistic. So a completely automatic process would be let me revise the process. Would be that to calculate, to get the medians of everything in the data frame, right? There are 12 or 11 columns. Maybe you can drop the, maybe you can drop the target, but you don't have to. If you confirm that there's no missing value from the target, you should not impute missing value to the target. In fact, there shouldn't be. It shouldn't be happening. So you calculate the median of the entire data set, which means all the columns, and then you should get, a bunch of medians, including the total sulfur dioxide, right? Once you have that, and then you call fill NA method of the entire data frame, and then provide the stats with all the possible medians. So what happens is here, the imputation is only going to happen for total sulfur dioxide, because there's no missing values on the other columns. But imagine if there is one missing value in fixed acidity, and there's one missing value in total sulfur dioxide, this step is going to use 134 as the imputation value for any missing values under total sulfur dioxide, and use 6.8 as imputation value for any missing values under fixed acidity. It's going to match and fill and will not mismatch. So this is going to be a very smooth process. After that, let's assign it to, according to the question, my dear, no NA, done without a problem. And then let's sanity check. The last step is, does my DF has any missing value? Because I suspect there is nothing there, I'm going to call the double sum, and I get 0. it's confirmed, the missing value is imputed. So that would be all that I plan to say. Let me stop the share and all right, any questions? If there's no questions, then Hackshot 4 is due by latest by end of today. Sooner the better, of course. And good luck. All right, I'll stay here for a little bit longer. But if you don't have any questions, feel free to, oh, there's a hand. Miguel, you have a question? Is that Miguel? Does that mean you have a question? Or not? Oh, okay. I should do. I go okay. So, oh, mic is not working. Question 10 and 11. Let's see. I would say, of course, I know. Let's see. Any particular issue? Question 10. Any particular issue? You can type. But I'm going to take a look here. I've started resharing the Jubilee notebook.
Is it?
All right. So question 10 asks you to fit a linear regression model and plot the result. The first step is to prepare Y data using the data set that has been imputed with the missing data imputed. Prepare Y data and then prepare X data using the 11. Okay. Prepare Y data here it simply means to extract the Y, the Y column. The Y is the target, right? Understand the data set first. You know, given the information here, know which one is the target variable, the Y data of all the 12 columns. There is no ID column, by the way. So prepare Y data means to simply get it and assign it to Y data. And with that, for the X data, you want to drop the Y data, right? And I believe that is mostly it. Let's see. Oh, I think question 9 does something here. So question 9, by question 9, you will have scaled, standardized the columns. So with that, your X data should come from the result in question 9. Whereas your Y data shouldn't have any preparation. Your Y data should come out of your original data set. So with that, and that process should be the same as the module demonstration, right? So with that, doing a linear regression by using stats models. But no, here this is using I believe it's using the what's the package by the way? Is using just the same one. The scalar, it is using the scikit-learn package here. Here the focus is not hypothesis testing, but rather it is more about the linear model, training the models and to evaluate performances of different. So follow the course material on follow the module mostly because in the linear model is in module 7.2. Yeah, and when you follow the slides, the hands-on Google Notebook go accordingly with the slides. So, switch back and forth to follow the process. And then only a standard process here is requested. So to train a linear model, a linear regression model, you would use a linear regression. The scikit-learn package linear regression. Here, let's see. That's question 10. The linear model, right? And then provide the X data and Y data, but do it under a cross-validation framework. So you will also make use of the cross-val score object, the cross-val score object to implement the training under the cross-validation framework. So in the end, you'll get a matrix of different evaluation results. And then use that data, you will expect to get a line. The same thing with the modules. You'll get a line. It's 10 cross-validation, 10-fold cross-validation. So you'll get a line of with 10 points connected by lines. So it plots the here it's the errors. It's the error performance of here, the negative mean, the error performance of the model on the 10 folds, following the cross-validation process. So you'll expect, a line. For this part. So that would be question 10. I would say the examples provided by the module is very easy to implement here without too much complications. Now for question 11 is the other algorithm, k-nearest neighbors. For k-nearest neighbors here, it gets a little bit more complicated. So spend more time to digest the process. And then the difference here is mostly you will need to adjust the weights. Because of this k-nearest neighbor. And here it I think it uses the distance weighted. Let's see. You use the k-nearest neighbors, k-neighbors regressor, and the weights is distance. So it's distance weighted weights. in calculating the in for the algorithm to determine which points are selected. But the coding doesn't have to touch that technical level. But make sure that you follow the materials in the module. And then for part 3, you would expect a line for ups and downs, a line with 7 dots, a line with 10 dots, and then lines connecting the dots to that plots the errors here, the same kind of error, negative mean squared error. It's not mean squared error. We said earlier, mean squared error would be positive, but the negative mean squared error would be the opposite of error, which means the performance. So higher the better. You will expect the line to display different heights, and then the points will reflect different heights, and then the lines will connect them. So some variations across the 10 folds. Okay. Okay, hopefully that gives you a little bit of a heads up. We have another question. Can we z-scale? Can we z-standardize after dropping the target variable? So I believe that's what question 9 is asking. Question 9 asks you to z-standardize all 11 input variables. Remember, there are 12 variables in the original data set, right? And then one of them is the target. So for question 9, you should, as you said, you should drop the target variable before you do standardization, before you do the scaling. That is right. That is right. All right. Let's see. All right. If not any more questions, then we can call it a day, and then gives you some time to focus on the hack shop. Make sure you turn in the hack shop by the end of today. And if you have more questions, text me in chats, and then make sure you include TA as well. We make the best team, so either one of us can answer your question. No very last minute questions. So if you have questions, better ask early, right? No midnight questions. 11:59. Would you really expect something that will be helpful in solving an error? And that last minute will be only last minute questions. If Blackboard is done.
Professor, I just have one quick question.
Sure.
So for question 11, in order to find K, do we need to add 1 into the formula?
So I see where your question is. That won't be necessary for Python. And your question may be because of the other course that you used to SAS, or maybe irrelevant. But here, let's say pick K. I mean, K doesn't have to be unique. Unique labels. And in general, K would be quite different from 1. So it's not going to be very small. Use the rule of thumb that's talked about in the post materials. It's typically, away from 1. So the problem of the issue of, sometimes algorithms include the point itself as part of the K. It wouldn't be an issue here. And also, you are not asked to identify those labels from the result. So the answer would be no. You don't have to.
All right, thank you so much.
Sure. Great. All right. We can close this meeting now. Let me stop sharing. Let's call the meeting. Adjourn the meeting for now. Send me messages if you have questions, include TA as much as possible. And then I'll see you in 2 weeks for our last meeting before final. And again, now would be the time to start working on the projects and let us know if you have any questions. All right. Enjoy the rest of the night.
Thank you. Goodbye.
Bye.
Thank you.